Last time we talked about the two remarkable phenomena that make single particle CryoEM structure determination possible. This time we're going to talk about two main problems that really limit the applicability of the method. The two severe problems are, first, that CryoEM images have very low contrast, and second, that radiation damage limits the number of imaging electrons we can use, which means that there's a lot of noise in the images, and that limits the signal-to-noise ratio. So the low contrast comes from the fact that we only have phase contrast from the relatively low atomic number atoms in biological samples. So what happens is an incident electron that passes near the nucleus of an atom experiences a positive potential, and that positive potential causes a very small phase shift in the electron wave. And it is this phase shift that we're going to use to get contrast in our images. So if we have an object, there is a three-dimensional map, a projection of it, of the TRPV1 channel protein. And here's a simulated microscope image, and as we bring the microscope into focus, you can see that the amount of contrast that we get from this specimen is very low. What I've shown here, I've actually plotted the density across these lines in these images so you can compare the very low contrast of the in-focus image with the original density map. So people can get more and better contrast by defocusing the microscope. So if we go from, say, 90 nanometers over focus now down to about 90 nanometers under focus, we get to a place where the material science people like to work. That is a focus setting that preserves high-frequency information the best. It's called the Scherzer defocus, and you can see that even so, we get a fairly small amount of contrast. So what people in CryoEM do is that they proceed to use even larger amounts of defocus. It's better to do so-called underfocus, which means weakening the objective lens current. And the more underfocus we make, the more contrast we actually get in the acquired image. So we can go even to higher defocus values and get more and more contrast, but you can see what's happening here. We're getting what's called image delocalization, whereas the object itself is bounded here within plus and minus 50 angstroms, and our x-coordinate here, high frequency, high resolution information has been spread out, has been delocalized from the center of our particle. It turns out that this delocalization can be undone computationally, but in the end, we get less contrast than we could if we had a perfect phase contrast microscope. This is why there's a lot of interest in phase plate technology, which we'll talk about later, but at the moment, most CryoEM images are taken with this kind of defocus contrast. And that contrast is lower than it theoretically could be, and of course it's the low contrast of the objects that we are taking pictures of that contributes to the low signal-to-noise ratio. Now, the second problem is radiation damage. By radiation damage, I mean interactions between the imaging electrons and the proteins, macromolecules in the specimen that actually damage the macromolecules. So physicists talk about two kinds of interaction events. There's so-called elastic scattering, where an electron preserves its original energy but has its phase shifted by interaction with an atom. And there is so-called inelastic scattering, where an incident electron interacts with another electron in the specimen and knocks that electron, for example, out of the orbital of one of the atoms, And the secondary electron can then move through the specimen and cause damage, breaking covalent bonds and basically starting to incinerate the macromolecule that we're trying to take pictures of. And unfortunately, inelastic scattering events occur more often than elastic scattering events. It's the elastic scattering events which are the ones that are going to give us our images. Richard Henderson, the third of the three people who got the Nobel Prize, was one who considered carefully what is possible with the electron microscope. And he shows that electrons are much better than X-rays in two respects for imaging single particles. First, electrons have a cross-section, that is a probability of interaction with an atom that is many orders of magnitude higher than that of X-rays. And that means that electrons interact strongly with matter and are appropriate for things on the order of 100 nanometers in size and not appropriate for much thicker specimens. The other thing is that the ratio of inelastic to elastic scattering is more favorable in the case of electrons than to X-rays. And this is even neglecting the fact that inelastic scattering events in X-rays cause much more radiation damage. So in both cases, the inelastic scattering probability, that's denoted by these upper dots, is larger than the elastic scattering probability. Nevertheless, we get elastic scattering events, and those are the events that give us contrast. But clearly, we cannot deliver too many electrons, or we will, in fact, burn up our macromolecules before we've gotten a decent picture of them. Here's a quantification of this by Grant and Grigoriev. Here they are estimating the amount of signal at different resolution ranges remaining in a sample as a function of the accumulated electron dose. And you can see that especially for maintaining high resolution information, so this is a curve of 4 angstrom resolution, you can see that the signal decreases by about an order of magnitude for every 10 electrons per square angstrom of accumulated dose. So that means that we cannot use very many electrons per square angstrom of specimen area. And of course, if we are using a small number of electrons, that means our detector is going to accumulate a small number of electron counts. And by counting statistics, that means that there will be a considerable variation even in a field that otherwise would be of constant illumination just due to counting statistics. So in summary, there are two severe problems in single particle cryo-EM structure determination. The images have low contrast, and radiation damage means that we can only use very small electron doses. And the low signal to noise ratio means finding particles in the first place, and determining their orientation becomes more and more difficult, especially when the particle, that is the macromolecule that we're looking at, is small. And so the signal to noise ratio really sets a lower bound, sets a lower limit on the size of macromolecules whose structure can be determined.